Welcome to MOOC Interactomics course. After discussing SPR and SPR based techniques, in today's lecture we will now discuss about some ellipsometry and interferometry based techniques. We may not be able to cover all the label free techniques in details, however, we will at least talk about some of the promising label free platforms and also give you an overview of the whole field. Ellipsometry is based on the polarization state of the reflected light, which is altered due to the changes in the dielectric property or the refractive index of the sample surface. The imaging ellipsometry combines ellipsometer, microscopy and CCD camera, which can measure the total protein content on solid surface. In this slide, I have shown you a configuration for ellipsometry based label free technique. A monochromatic laser light linearly polarized by the polarizer is passed through a compensator to produce elliptically polarized light. This light is reflected from the sample surface and again becomes linearly polarized, which is detected by an analyzer filter, and this reflected light intensity is monitored with a photodetector. Ellipsometry based approaches has many merits. The instrumentation is very simple, which is unlike the SPR based instrumentation. It is not restricted to the gold or silver surface. It is more economical than previously discussed SPR based techniques. It provides high throughput capability with simultaneous measurement of an entire microarray. The demerit of the approach is its sensitivity. It is less sensitive than SPR or SPR imaging based techniques. Let us now discuss a few applications based on ellipsometry platforms. Ellipsometry has been successfully applied for many applications such as biomolecular interactions, hormonal activity, cell factor, receptor binding, diagnosis for hepatitis B, kinetic measurement of multi-protein interaction processes and quantification of competitive adsorption of proteins. The combination of imaging ellipsometry with microfluidic system can provide many advantages, which are not possible to obtain from any individual technique, and this configuration, the combined imaging ellipsometry and microfluidics, has been applied for the real time measurement of binding kinetics for SARS virus. Let us talk about oblique incidence reflectivity difference or OIRD. OIRD is a form of polarization modulated imaging ellipsometer in which the harmonics of modulated photocurrents are measured under the suitable nulling conditions. It can be used for label free high throughput detection of biomolecular interactions on DNA as well as protein microarrays. The changes in the thickness or dielectric response due to a reaction such as protein binding can provide a detectable signal, and that is how the reactions can be monitored. In this slide, I have shown you the configuration of OIRD. In the scanning OIRD microscope, the X scan is performed by moving the sample holding stage, and Y scan is performed by combination of rotating mirror and theta lens. The sample is coated on the glass slide, which is directly in contact with the fluidic system. The OIRD platform is more sensitive than imaging ellipsometry. It provides a rapid and high throughput affinity detection system with real time measurement and detection, whereas its demerit involves insensitivity to conformational changes. OIRD has been used for various applications. The OIRD microscope has been applied for real-time monitoring of antigen-antibody interactions, nucleic acid hybridization and protein small molecule binding reactions. There are various applications of OIRD which makes it a good choice for label-free detection of proteins on microarrays. We have discussed that label-based methodology is widely used for microarrays, but just to avoid the issues because of tags and labels, there has been more inclination now to couple the microarrays with the label-free platforms, and that is why we are looking at different types of emerging label-free platforms which could be coupled along with microarrays such as SPR imaging, ellipsometry, OIRD based methods which are trying to utilize the benefit of both microarrays and label-free detection system to provide high throughput data without interference of a tag. We have already discussed about SPR and imaging based techniques, ellipsometry based techniques, and so now we will talk about interference based techniques. Let us first talk about interferometry. Interference based detection techniques are powerful tool for biochemical and functional analysis of proteins. Its basic principle is transformation of phase differences of wavefront into observable intensity fluctuation known as interference fringes. There are many promising interferometry techniques that have emerged, which includes spectral reflectance imaging biosensor or SRIB, dual channel biosensor, SPR interferometry, on-chip interferometry back scatter detection and biological compact disc, BioCD, etc. Let us look at the interferometry principle in detail here. In interferometry, the phase difference of wave fronts are transformed into observable intensity fluctuations, which is known as interference fringes. The interferometry techniques relate the optical phase to biomolecular layer density on the surface. The signal is created by additional phase shift or optical path length difference, which is caused by the adsorbate biolayer. So, the biomolecules are printed on this surface. The left hand panel shows the unbound state, the right hand panel is showing the target protein bound state. The optical path length difference, which is caused because of target protein binding to the biomolecule printed on the surface, is measured here. One of the interferometry technique is BIRC or back scattering interferometry in rectangular channels. Let us briefly discuss this technique. This is a highly sensitive interferometry approach performed within rectangular channels of micrometer size, which are formed in inexpensive PDMS printed on surface. Here is a configuration of BIRC. The micrometer sized rectangular channels are modulated within the PDMS chips, and this interferometry principle is applied here for measurement of interference due to the biomolecular interactions. BIRC has been applied for many versatile applications, demonstrating the power and versatility of the approach for detecting protein ligand interactions in complex environments. It is highly sensitive approach which requires only minute amount of material. This technique facilitates the label free studies using very small picoliter volumes with a potential to quantify binding affinities in a high throughput manner. Similar to other label free techniques which we have discussed, BIRC also provide a real time measurement of molecular interactions, and it is applicable for reversible and irreversible protein-protein interactions. The technique is very cost effective. However, it has some demerits such as use of PDMS chip, multi-step surface preparation and time consuming and complex assay procedure. Let us now discuss about a spectral reflectance imaging biosensor or SRIB. It is a label free approach which is also based on interference. The changes in optical index as a result of capture of biological material on the surface can be detected by using optical wave interference. SRIB monitors molecular binding interactions directly. As shown in this slide, the principle of SRIB is discussed. The interference of light reflected from the silicon dioxide surface increases the optical path length difference, which is caused by the biomolecular binding, which in turn is measured by a spectral reflectance imaging biosensor. Similar to some of the other recently discussed label free techniques, SRIB is also very useful, but recently introduced, which has been applied to study dynamic protein-protein and protein-DNA interactions. The simplicity of the system, its high sensitivity and compatibility with glass surface chemistries makes it a very promising platform for multiplexed detection of different biological analytes in complex samples with critical impact in research and diagnostic applications. This technique has also proven to be a powerful tool for microarray applications for high throughput capability. The spectral reflectance imaging biosensor are cost effective. They are used for rapid determination of binding kinetics. They can be easily implemented, providing high throughput data for biomolecular interaction studies. Its demerits include its suitability for only smooth layered substrates and some non-specific binding issues which need to be improved with advancement of this technology. Let us see this animation to further understand the principle of SRIB. A spectral reflectance imaging biosensor or SRIB. In SRIB technique, a silicon dioxide coated silicon surface is functionalized with biomolecules of interest. The magnitude of total reflected light at a particular wavelength depends entirely on the optical path length difference or OPD between the top surface and the silicon dioxide silicon interface. As you can see here in this animation, when the biomolecules are printed at different depth, that difference in the optical path difference is measured here on the silicon dioxide and silicon surface. Binding of the target to the immobilized biomolecule further increases the optical path difference, and it is shown as a shift in the spectral reflectivity. The spectral reflectance imaging biosensor or SRIB therefore serves as a useful tool for high throughput real time detection of biomolecular interactions. After discussing many label free techniques, now I am going to show you an overview of some of the sensitive label free platforms which have potential to be coupled with microarray applications. Though we have discussed some of these approaches and principles in detail, it was not possible to discuss these in context of microarrays. Also, there are some nanotechniques based label free methods which we will discuss in our subsequent lecture, but some of the label free techniques shown here are very promising for high throughput protein microarrays or DNA microarrays based applications. As you can see in the panel A, on top is based on Raman labels based on multicolor single bond nanotubes tagged for the multiplex protein detection. The panel B is surface plasmon resonance, which measures change in the refractive index along with a sensogram, which is shown in bottom of the same image. Panel C displays the real time multiple binding events by monitoring the intensity of EOT or extraordinary optical transmission through the nanoholes sensing arrays. The panel D describes SRIB, as we talked earlier, is based on the light reflected from the silicon dioxide surface. Panel E shows a planar waveguide array system for fluorescence imaging. Panel F shows nanowire sensor arrays where proteins bind specifically to its receptor on the nanowire and produces change in the conductance. So, the slides provides you an overview of various platforms which are currently in progress for coupling with the protein and DNA microarrays, so that one could utilize the potential of both the label free detection as well as microarray capability. It just shows that there are many new label free techniques which are emerging for different applications. Some of these are at very early stage of development, and it has only been tried on the concept level with tried tested pair of proteins and antibodies. So, applications based on the real life examples, the actual clinical samples, etc., are required for showing the strength of these technologies. Most of the applications and studies have only shown the proof of concept, but not the biological meaningful applications. SPR is one of the well established technique which has been discussed in detail. There are many other emerging label free techniques such as biolayer interferometry, for which we would cover the details in subsequent lectures. In summary, till now we have discussed about various label free techniques including SPR based approaches, ellipsometry based techniques such as OIRD and imaging ellipsometry, and interference based detection techniques such as BIRC and SRIB. Thank you.